Previously, we used a chi-squared test to indirectly test whether two population proportions were equal. Now I would like to propose a test in which we directly compare the two population proportions. So I want to start with a general 2 by 2 contingency table that has two samples, sample 1 and sample 2. Okay, y1 will be the number of individuals that have a particular trait, and then n1 minus y1 is going to be the number of individuals that do not have that trait. So we have a dichotomous population for sample 1. The total number of individuals in sample 1 would then be n1. Now for sample 2, y2 is going to be the number of individuals that have that same trait. And then n2 minus y2 is the number of individuals that do not have that trait. Again, we are forming a dichotomous population with those two samples. And then the total number in sample 2 is going to be n2. Now we used a chi-squared test to determine whether the estimated probabilities of p1 hat, which is y1 over n1, and p2 hat, which is y2 over n2, differ enough to conclude that the true probabilities, p1 and p2, are not equal. I'm going to propose an alternate test in which we actually construct a confidence interval for the difference between the two population proportions, p1 and p2, and use that to determine if there's a significant difference between p1 and p2. Now, you see that I listed here p1 hat and p2 hat for simplicity, but you'll remember that we actually adjusted our population proportions using a Wilson adjusted population proportion formula. So I'm going to remind you that we previously adjusted the population proportion by adding 2 successes and 2 failures to our dichotomous population, so that p tilde, when I adjust it, is y, the number of individuals with that particular trait, plus 2, that additional that I'm adding with that trait, over the sample size n, plus 4 total individuals that I'm adding to the sample. Now I want to take those 2 successes and 2 failures and spread them amongst the 2 samples. So based on this idea, we will add 1 success and 1 failure to each population proportion. Then p1 tilde will be y1 plus 1 over n1 plus 2, and then p2 tilde will be y2 plus 1 over n2 plus 2. And you can see that I've added 2 individuals to each of the samples, there being 1 success and 1 failure to each of the samples. Now I need to find the standard error for the difference between those 2 population proportions. So I'd like to incorporate some ideas from section 6.6, which is when we were comparing the means of 2 samples, and then also from 9.2, where we define the standard error for a population proportion. So you're just going to recall here that the standard error for the difference in 2 means was defined to be the square root of the sum of the standard errors for the individual groups. But when we were looking at standard error for population proportion, we'll recall that that was the square root of p1 tilde times 1 minus p tilde over n plus 4. So I'd like to combine these 2 ideas to come up with a new formula for standard error. And so that formula for standard error will take the square root of the sum of the squares of the standard errors for the 2 populations. So here it would be p1 tilde times 1 minus p1 tilde over n1 plus 2. Okay, because when I adjusted my population proportions, I only added 2. So I'm going to add a +2 there instead of 4. And then I'm going to do P2 tilde times 1 minus P2 tilde divided by N2 plus 2. And so that will give my standard error formula. So working with a population proportion, our 95% confidence interval will be based on the normal distribution. So we want to take our difference in population proportions, P1 tilde minus P2 tilde, and they're going to do plus or minus 1.96, okay, which is representing our middle 95%. And then I'm going to multiply that by standard error, which is the square root, again, of P1 tilde times 1 minus P1 tilde over N1 plus 2, and then add P2 tilde times 1 minus P2 tilde, and then I'm going to divide that by N2 plus 2. And then if our 95% confidence interval does not contain 0, that means that there's no overlap between the two population proportions and we can reject the null hypothesis. So this is very similar to what we did when we were comparing two means. Now, it turns out that this test is going to be approximately equivalent to the 2x2 contingency table. Okay, so the chi-squared test for a 2x2 contingency table is approximately but not exactly equivalent to determining whether the confidence interval contains 0. Okay, so in most instances, if the confidence interval does not contain 0, then the chi-squared test, you would be able to reject the null hypothesis. But there are a few instances where the confidence interval, say, would be very, very close to not containing 0 or containing 0, and then you would get the opposite conclusion of the chi-squared test. But again, for the most part, these two tests are equivalent. So I would like to do an example. Okay, I'm going to compute a confidence interval for the difference in two population proportions for our liver disease data, where we have individuals who do and do not have liver disease, and then we have those who drink and do not drink. Okay, so our first population proportion is going to be those who have liver disease amongst the drinkers. Call that P1 tilde. That's going to be 63 plus 1 over 744. Sorry. Copied that wrong. 807. That's the number of drinkers plus 2. And that's approximately 0.0791. Okay, so 7.91% of the population, okay, has liver disease. 7.91% of the drinkers have liver disease. So for P2 tilde, okay, those are the non-drinkers that have liver disease. Okay, so I'm going to take my 7 non-drinkers that have liver disease and add 1 to that. Out of my total number of non-drinkers, which is 193, and now I'm going to add 2 to that, and that's going to tell me that 0.0410 is going to be the proportion of the non-drinkers that have liver disease. Okay, now that I have those two population proportions, I would then find the standard error for the difference between the two population proportions. That's going to be the square root of, let's see, 0.0791 times 1 minus 0.0791 divided by 807 plus 2. And I'm going to add to that 0.041, that's the second population proportion, times 1 minus that. And I'm going to divide that by 193 plus 2. When I work that out, I get 0.01708. Okay, so the standard error for the difference in these two population proportions is about 1.7 percentage points. Okay, so my 95% confidence interval that's going to be the difference in the two population proportions, so P1 tilde minus P2 tilde plus 1.96 standard errors. Okay, that's going to be the difference in the population's proportions. It's going to be 0.0791 minus 0.041. And then I'm going to add plus or minus 1.96, okay, to times 0.01708. That gives me a confidence interval of 0.0046 to 0.0716. And that does not include 0. Okay, so that tells me that there is a difference in the population proportions. Okay, that does agree with what I had done with the chi-squared test, where I was able to reject the null hypothesis and say that liver disease does depend on drinking status. Okay, so we would say we are 95% confident that the proportion of drinkers with liver disease is 0.46 to 7.16 percentage points higher than non-drinkers. So not only can we say that there's a difference in the population proportions, but we can say that the proportions of drinkers with liver disease is a certain number of percentage points higher than the non-drinkers. I'm going to conclude this video with just some reminders about when you can apply this theory, where you can do, say, chi-squared tests using 2x2 contingency tables. Okay, so let's remember that experimental design is that the data must be able to be viewed as one categorical variable with two random samples, or two categorical variables with one random sample. And all observations within a sample must be independent of each other. The sample size, the expected frequency of each observation in a contingency table should be at least 5. Okay, so you don't have the number of observations have to be 5, but the expected frequency of every observation, which generally appear in those parentheses in the 2x2 contingency table, those have to be at least 5. Now, if you have a larger contingency table and you have observations with expected frequencies that are not at least 5, you can pool together categories with small frequencies to make sure that the expected frequencies are at least 5. Okay. The null hypothesis for this test is that the row variable and the column variable are independent. And then an important note is that a small p-value can only apply a causal relationship if the data arise from an experiment with a random assignment of treatments. Okay, so if you have, say, a placebo group and then an experimental drug group, then you can use chi-squared to infer a causal relationship, as long as when you assigned people to the two groups, it was done randomly. Okay. Otherwise, when you have those 2x2 contingency tables and you're analyzing the data, you can only refer that there's an association between the two groups, not by chance, but you cannot say that there's a causal relationship unless you have that particular experimental design. Okay, I want to give some examples of dependent samples that you can read in the book in section 10.6. Okay, so we needed the observations to be independent of each other. So when do you have dependent samples? One example in the book talks about finding food preferences for insect larvae where observations were made within 6 petri dishes. And so what you had is a lot of insect larvae inside each of the 6 petri dishes, and then they were looking at whether they preferred one food over another inside that dish. Okay, but all of the individuals within the dish are going to be dependent because they're going to see what their neighbors are doing. And so really they had 6 observations instead of the total number of insect larvae. Okay, so that is a mistake that you wouldn't want to make about independence. Another one is the pollination of red versus white flowers by hummingbirds, where multiple flowers from the same plant were observed. Okay, so here again, if you have multiple flowers on the same plant, okay, then each plant is one of your observations, not each of the flowers. Okay, if you want to be able to run one of these tests and you have independent samples, then you need to test different flowers from different plants and not assume that different flowers on the same plant are independent. Okay, and there's a warning here that assuming dependent samples are independent can lead to p-values that are artificially small. Okay, so we don't want to inflate our sample sizes with dependent samples. And that concludes when you can apply a chi-squared test.